these. They never show it like for a really long time. 1, 8, 20 something, 28, 56 something, 0, 70. Yeah. So our thing is working. I declare. The next thing we're going to do, it's a bit more like on the mathematical level. It's maybe less common of an operation, but in the computer, if you add two really big polynomials and lots of higher terms cancel, you wanna so you have a bunch of zeros. You want to clean that up. So you want to reduce the degree to the actual degree. So and this is something I think that you do to a specific polynomial. It's basically something that you need to do for the n to correctly track the degree. If p.coef p.n minus 1. Okay, this is supposed to be the last term. Yeah. Oh, right. In C, you need to do this. So now instead of passing as input a polynomial, I'm passing a pointer to a polynomial. I'm passing the address of a polynomial, and I'm going to modify rather than produce a new thing. So this arrow means follow the pointer. So go to the address and then look at that specific part of the thing you find. So p arrow n means p is a pointer and you want to do p.n, but p is a pointer and c makes you do this. So this is saying while n is not equal to 0, look at the biggest term if it's equal to 0. Might not be exactly equal to 0, but I think that if it's not exactly equal to 0, we should just assume that it's a meaningful value, because it's very hard to be in the business of saying, okay, that value is really, really small, so it's probably 0. So we'll just forget it, set it equal to 0 perfectly. It would screw up other properties of polynomials. So if it's exactly equal to 0, for example, if you made the same polynomial twice and you subtracted one from the other, it would be exactly 0, hopefully. In that case, basically, you have to change n. You have to decrease n by 1. And if it's not, if you find something that's not equal to 0, then you simply stop. Because if you don't do this, what will happen is that, say you have 1, 0, 0, 1. Well, you're going to say, okay, 1 is not equal to 0, fine. I loop again, 0 is equal to 0, okay, so then I reduce the degree by 1, 0 is equal to 0, reduce the degree by 1, and then 1, so you get, instead of keeping 1, 0, 0, 1, you get the polynomial 1, 0, so just a constant 1, which is wrong. It's very wrong. But if you do this, it means that the first time that you find something that is not equal to 0, you stop trying to reduce the degree. You break from this while loop, and yeah, that's what this does. Let's add poly p with const mult -1 p, right? Oh. Okay, you get this, and now if we reduce the degree of p, but you can't pass p because p is a poly, you need the address of p. You see, it compacted it, so that exactly being 0 like that. It means there's in the eye of the program, when you add the other the polynomials, or you multiply, you don't look into the array. We could also it's funny because the to-dos I put is basically the things I'm not going to do. We could also look at freeing the memory and reallocating the coefficient array after reducing degree. And when we add poly, that is pretty much the only operation so far that can reduce the degree. So if we put it here, and whenever we add, just before we add, we can say reduce the degree of sum. So if we reduce the degree every time we make a sum, we're never going to lose the sync between the actual degree and the degree that's advertised by the n value. As a further optimization,